Hi, and welcome to my talk. This is joint work with my supervisors, Kevin Layton Brown and Hu Fu. Imagine that you're an instructor in a course and you want to teach your students how to write a proof. One of the best ways for students to improve their proof writing skills is to practice them over and over again. But if you're teaching one of those large university classes, that means you're going to need a lot of TAs who can read students' proofs for you and provide them with feedback. However, most universities do not give as many TAs as instructors hope for. A proposed solution to this is to use peer grading, which is to ask the students to grade one another. Peer grading can have several advantages. It offloads the grading workload to the students and therefore makes courses more scalable. It provides much faster and more detailed feedback to students because now each student is grading only a few others as opposed to a TA who would normally be overwhelmed by grading so many students. It also provides this opportunity for students to think critically about the work of one another and learn from that. However, any experienced teacher would tell you that without a proper mechanism that incentivizes students to take their grading tasks seriously, peer grading would not be effective in practice. Several approaches have been suggested to overcome this incentive issue. One of the most prominent ones is to give each assignment to multiple students and reward them based on their behavior. Now, when this was initially suggested and most of the subsequent work would incentivize accurate grading in equilibrium. In a classroom setting, this means that each student would only prefer to be an accurate grader if all other students are doing so as well. And in a large classroom scenario, this might not be a realistic expectation because students are so diverse. More recently, there has been some really nice follow-up works that would provide much stronger incentives for students, but they have their own limitations. For example, they may require students to do multiple tasks and also apply the same strategy across different tasks. The approach that our group has been taking for the last several years, both in practice by implementing a peer grading software called Mechanical TA and also in theory, is spot checking. Spot checking mostly makes sense in scenarios where the instructor does not have enough power to grade everything, but still has some limited access to some TAs. And therefore, those TAs can randomly check the performance of a subset of students and reward them accordingly. Previous work has shown that if you spot check a sufficiently large fraction of students, you could provide them with one of the strongest theoretical guarantees that you can hope for, which is to make accurate grading the dominant strategy. But let's remember that spot checking can be expensive because it requires TAs. But previous work only considered spot checking with a fixed probability. So it's kind of natural to start to think about if there is any way to spot check in a smarter way. While there can be many approaches to think about this question, in this work we're going to focus on spot checking based on what the students report to the system. We call these mechanisms report-sensitive spot checking mechanisms. The intuition behind this is that imagine an instructor has given a really hard problem set to students, but all the reported grades are really high. I think we can all agree that this is a bit suspicious and you might want to spot check that with a higher probability. There are two main takeaways that I want you to remember from this talk. First, report-sensitive spot checking can indeed help save TA costs while providing the same kind of guarantees as the fixed probability mechanism. Also, when there are two grades in the system, the efficient way to spot check students is to spot check them based only on their own reports. Okay, With this in mind, now let's get a bit more formal and take a look at our model. We assume that there is only one assignment in the system. In the case of having more assignments, we can just run our mechanisms in parallel. This assignment has a true quality that can be either bad or good. Here we denote them by B or G. And this row quality is drawn from a commonly known distribution, PRQ. There are n students in the system. Each student has several strategies. They can either choose to be truthful, meaning that they invest the cost C to observe a signal SI and report it. They can choose to still invest the cost to observe the signal, but report something that's different from what they observed, if they found this more beneficial. Finally, they can choose to not invest any effort and report an arbitrary signal to the system. In addition to the students, we assume that there is a TA whom, if consulted, would basically play as a non-strategic student in the system and always be truthful. We assume that student signals have the same domain as the true quality. These signals are independent conditioned on the true quality. And for the sake of this talk, I'm going to assume that all the signals are drawn from the same distribution. But in the paper, we extend our results to cases where all signal distributions can be different from each other. We consider two main groups of mechanisms in this work. The first one is called ROS, or report oblivious spot checking mechanisms, which is motivated by previous work and always spot checks students with a fixed probability. And the next group is RSS mechanism, or report sensitive spot checking mechanism, in which the spot checking can depend on the report of all the students. As for the reward function, we only consider the identity reward function, which basically means in our mechanisms the student is rewarded only if their spot check and the reported grade exactly matches the TA grade. Notice that here the reward is shown by a constant R, but ultimately the quantity that we're going to care about in the remainder of this talk is the ratio between this R and the cost of observing the signal. In our work, we focus on dominant strategy incentive compatible mechanisms, or DSIC mechanisms, which in the classroom scenario means that we want each student to prefer to be truthful no matter what all other students have decided to do. Also, our mechanisms are anonymous, meaning that they cannot identify students. As I mentioned before, we care about minimizing TA costs or TA workload. In the case of having only one assignment, the TA workload is basically the probability with which the TA needs to provide a signal, assuming all other students are truthful. And finally, we can set our goal to be setting spot checking probabilities such that this TA workload is minimized, and no matter what others do, each individual student would get a better expected payoff by being truthful other than playing any other strategy. Notice that this optimization problem has two n decision variables and an exponential number of constraints, and such problems are usually really difficult to solve. To make things more simple, now let's think about a single agent mechanism in which there is only one grader and one TA. Now, because there is only one grader, we have only two decision variables, which is the probability of spot checking if the grader reports bad or B, and the probability of spot checking if the grader reports good or G. Now here, because there are only two decision variables, solving this optimization problem to find the optimal values is easy. And here we show that in fact these optimal solutions are proportional to the ratio of over reward, and also reversely proportional to observing the other signal. This matches with the intuition that if one signal is highly likely to be observed, you would want to spot check that with a smaller probability. Having this in mind, now let's think about a naive generalization of this single agent mechanism, which, even though there might be more than one grader, still only spot checks each grader based on their own reported grade. In fact, to get more formal, we define a new group of mechanisms which we call PRSS, or Personal Report Sensitive Spot Check Mechanisms, which spot check each student with a probability that only depends on the student's own report. Remember that RSS mechanisms in general could spot check students based on the report of all students and not just one. But we proved a theorem that says when the ratio of reward over cost is big enough, a PRSS mechanism that uses X star B and X star G to spot check is in fact the optimal DSIC RSS mechanism. And if this ratio of R over C is not big enough, there basically does not exist any DSIC RSS mechanism. The intuition behind this is that first we show we have a convex optimization problem, then we show that the PRSS mechanism that we just defined is a feasible solution to this optimization problem. Then we show that this proposed solution actually optimizes a relaxed version of this optimization problem. This relaxed version is derived by removing almost half of the constraints. Finally, we argue that because we have a local optimal of the original optimization problem, therefore because of convexity, we have the global optimal. We also run an extensive both experimental and theoretical comparison between different kinds of mechanisms in the paper, but here let me just mention one of them that we find the most interesting, which is to compare RSS and ROS mechanisms experimentally. Okay, in this plot on the x-axis, you see the ratio of reward over cost on a log scale. On the y-axis, you see the scaled RSS workload. This scaled RSS workload is basically the TA workload of the optimal DSIC RSS mechanism as a fraction of the TA workload of the optimal DSIC ROS mechanism. As you can see from this figure, as the ability of rewarding students increases, RSS mechanisms become more effective, and sometimes this effectiveness is really considerable. Also, as we get more accurate students, as the probability of observing the true signal given the grade increases, we observe that, again, RSS mechanisms are more effective. Alright, to conclude, we have investigated peer grading mechanisms with a focus on report-sensitive spot checking mechanisms, and we indeed have shown that such mechanisms can be effective in saving TA costs while providing the same guarantees as a fixed probability solution. We showed that when there are only two grades, the optimal mechanism is a parallelization of a single optimal single agent report sensitive mechanism. Let me just remind you that we have our own peer grading software called Mechanical TA. We encourage you to use it. It automates this whole spot checking feature. As for the future work, one is to generalize our result beyond the two signals. Our analysis was limited to having only two signals. We also think of prior independent report sensitive spot checking mechanisms, which spot check without knowing the prior. Thank you for paying attention to my talk.